discuss the rotor frequency. So here we'll discuss the rotor frequency. Now see rotor frequency, suppose the stator frequency is the supply frequency, and that is F1. So you know that if the frequency equals to Ns, that is the supply frequency equals to Ns P by or Ns P by 120, as it so here 120 Ns P divided by 120, whereas Ns is the synchronous speed. Ns equals to synchronous speed revolution. So this is synchronous speed in RPM. So that is the synchronous speed in RPM. P is the number of pole. P is the number of pole. So that is the supply frequency F1 we have taken. Next, rotor frequency. Rotor frequency. That is the F2. F2 is the rotor frequency. So we are going to determine the frequency of rotor or rotor frequency. So we are going to determine frequency of rotor EMF. Rotor EMF. I will determine frequency. So we know that frequency equals to speed, that is the synchronous field speed for the supply frequency. So here for the rotor, the speed will be relative speed. Relative speed between what? Say suppose we have stator and rotor. So this is the stator part. For an example, this is the stator part, and here it is air gap, and inside it is the rotor part. So in this air gap, the field speed in this air gap, the field is rotating at synchronous speed Ns. See, when it is connected with the supply, the rotor induced EMF will depends on the relative speed, because rotor is also rotating and field is also rotating. So the rotor induced EMF will depends on the relative speed between what? Between rotating flux and the rotor. That is the speed. So here the frequency F2, frequency is F2, and that we can write. That is the frequency of rotor induced EMF. F2 equals to, we can write pole, that is the number of pole, whatever the poles, and then we can write relative speed between what? Rotating flux. So rotating flux and the rotor structure. So this is the frequency divided by, so pole and speed, and divided by what? 120. Then we can write here P and the relative speed between rotor structure and the rotating flux. So rotating flux speed is Ns. This is the rotating flux speed in RPM, and Nr is the rotor speed in RPM. So that here we can write it, this one, Ns minus of Nr, and that is the relative speed divided by 120. Now we know that Ns minus Nr, the relative speed, equals to S into Ns, or this is also called a slip speed. So here we can write f of f2 equals to fp SNs by 120, and f2 equals to, that we can write p SNs. So that is S into, we can write this one as P E into Ns divided by 120. So here we can write f of 2 equals to, so from here we can write f of 2 equals to S, and this value is f of 1, that is the supply frequency. So that from here we can write that rotor frequency equals to slip into supply frequency. That is 4. So that is the relation. So from here, at standstill condition, what standstill condition means, nr equals to 0. At standstill condition, that is means nr equals to 0. If nr equals to 0, then slip S equals to what? Slip S equals to 1. So if you put here 0, slip will be 1. And if slip equals to 1, then f of 2 equals to f of 1. This is the one condition. And rotor running at slip S. So when rotor running at slip S, that means rotor speed is nr and slip equals to S. So rotor frequency will be S into f1. That is that. So we'll discuss the rotor induced EMF. So far we know that at standstill condition, that is basically nr equals to 0. Nr means rotor speed is 0 and slip equals to 1. So at that instant, the relative speed, so you can write a relative speed between rotating magnetic field and rotor structure is ns, and that is the maximum speed in rpm, revolution per minute. So that as the relative speed is maximum at the time standstill condition, when the rotor speed is 0, or this is the condition, or we can say this is the condition this is the condition, this is condition of starting instant. Induced EMF of rotor E2 this is the starting instant, rotating relative speed in between magnetic field and rotor structure is maximum, that is the ns. So the induced EMF at the rotor conductor is E2, which is also a maximum. But when the rotor, but at any slip s, but at any slip s, relative speed will be how much? Relative speed equals to s into ns in rpm. So that we can write here, when ns is the speed, relative speed, induced EMF in the rotor conductor is E2, whereas 1 revolution per minute the induced EMF will be E2 by ns, and when the relative speed is sns and induced EMF will be sns E2 by ns, that is s E2. So induced EMF in the rotor, so that we can write here induced EMF of rotor conductor, okay, say conductor at slip s equals to SE2, and we know that E2 equals to 4.44. This is winding factor, Kw2 is the winding factor, F2 is the rotor frequency, N2 phi. So whereas this is the standstill, this is the induced EMF at nr equals to 0, slip equals to 1, and F2 equals to F1, that is the rotor frequency equals to supply frequency. So at slip S, the induced EMF will be SE2, and that is 4.44 winding factor, and then it will be F2 value will be, can write SF1 into phi. So here is F2 equals to SF1. Now we'll discuss the rotor leakage reactance. So rotor leakage reactance. So reactance X equals to, that already we know, omega L, and the rotor reactance, if we consider the rotor leakage reactance equals to X2. So X2 can be written as 2 pi omega, or directly you can write omega L. So omega is the angular frequency, and that can be written as 2 pi F2 into L. So L, suppose the rotor inductance L2, and the frequency. So that means the rotor reactance depends on the frequency, that is the rotor frequency, and there is a relation between rotor frequency and the supply frequency, that already we know. F2 equals to, that is the rotor frequency, equals to slip into supply frequency. So what will be the reactance at any slip S? Rotor reactance can determine at any slip S, at any slip S. So any slip S, X2, that will be SX2 and 2 pi, and this is SF1 L2. or that we can write 2 pi f1 L2 at standstill standstill. So this equation will be 2 pi f1 L2 into s. So whereas this is x2 and this is the s, so this is written here s x2. So rotor reactance at any slip s, this reactance will be s into x2. So next is impedance. So what will be the impedance? So Z impedance equals to, that already you know, R jx. This is the complex form of the impedance, and so here Z is the impedance, the rotor circuit. Suppose this is the Z2, R2 is the rotor resistance, plus jx2 is the rotor reactance, leakage reactance. So total impedance of the circuit, rotor circuit, the magnitude of the Z will be root over of R2 square plus x2 square. So this is the impedance at standstill condition. At standstill condition. But at slip S, rotor impedance Z at slip S, the rotor impedance will be root over R2. So this is R2 square plus S x2 square. This is the rotor impedance. So what will be the rotor current? Next is rotor current. So we know that basic is current equals to voltage divided by impedance. So rotor current I2 equals to the voltage, and here voltage is SE2, and impedance R2 square plus S x2 whole square. So this is the rotor current at slip S. So at standstill condition, rotor current I2 equals to, S will be 1, so you can write E2 divided by root over R2 square plus x2. There will not be a S, so this is x2 square. So this is the rotor current at standstill condition. So here we have two conditions. One is, so what we have seen here, that is one at standstill and at slip S. So what I've seen at standstill, rotor frequency rotor frequency equals to F2 equals to F1. At slip S, the rotor frequency will be F2 equals to SF1. Number one. Number two, next we have say induced EMF. So rotor induced EMF E2. At slip S, it is SE2. Rotor leakage reactance x2. At sleep S it is x sx2. Rotor impedance that is Z2 equals to root over R2 square x2 square, whereas here it is Z2 equals to root over R2 square plus sx2 whole square. Rotor current I2 equals to, at standstill, E2 divided by root over R2 square plus x2 square, whereas here it is I2 equals to SE2 divided by root over R2 square plus sx2 whole square. So these are the parameters of the induction motors. At standstill condition means when rotor is not rotating, that means NR equals to 0 at the time of starting, at the time of induction motor starting. And at sleep S, that means when rotor is running at the speed of NR. So these are the parameters we derived.